I think everybody has done the now. So, taking that I have all the tests here, I can now tell you what I think you should have been trying to answer. And the question is, what does this Fourier transform describe? Power spectrum? No. The autocorrelation functions? Not at all. Its imaginary content? No. However, it does describe the frequency content of a specific function. And this does so in a very fine and detailed fashion. Convolution of a function, f with a function g, describes the correlation between f and g. No, that's not true. Does describe the similarity between f and g. No, that is not true either. It requires the arguments of f and g to go in the same direction. No, that's wrong, that's for the cross correlation. It does require the arguments of f and g to go in opposite directions. True or false? Convolution or multiplication of f and g are the same thing. They are not the same thing, quite the contrary. You can find them either on either side of the Fourier transform. So they are not at all the same thing. A Fourier transform turns convolution into multiplication. Yes, that's what it does. And convolution evaluates the power spectrum is bullshit. And so is convolution of f and g delivers the autocorrelation function of f times g. It doesn't either. True or false? A Fourier transform is an exponential operation. You might think so, but it is a cos transform and a sine transform. Separately, only described in a rather weird notation. But it is a cos transform and a sine transform. And those are not exponential operations at all. In fact, they are not a quadratic operation either. They are a linear operation. A Fourier transform is therefore not at all multiplicative. A sinc function is used for transformation to complex. No, it isn't. It's used for cross correlation. No, it isn't either. For autocorrelation then? No, it isn't. It is the key interpolation function. It is the way in which you can interpolate a sampled function at equidistant samples. You can interpolate all the between. Have properly is at Nyquist frequency or faster, then the sinc function helps you to get all the points in between at any detailed accuracy that you would. True or false? A Fourier transform is even. No. A Fourier transform is even and odd. A convolution is even. No. Convolution again is even and odd. An autocorrelation is even. Yes, it is. And the cross correlation is not. Doing interferometry requires slits. No, that's a bit exaggerating. In fact, or hardly ever use it with slits. We will use elements. So that is not very likely that we want that. Autocorrelators. An autocorrelator here and an autocorrelator there. That's something like getting a power here and a power there, and what do I do for the cross correlation? So that's not it. I need cross correlators, and cross convolvers are bullshit. So I do need correlators. That was it. I hope you agree with me that it was not that hard and difficult. It's sort of in line with what we tried to transfer to you yesterday. So, we finished off yesterday with a sampling function. And that was in fact the most interesting sampling function. Of course, sampling functions are extremely important. They describe how you take readings, a digital process, you convert from an analog process. From an analog process you convert to a digital process by having this analog signal be read sufficiently often. If you read it not often enough, then all this time that this signal is there and you're not looking, your telescope is blind, so that's bad. You must read it sufficiently fast. And sufficiently fast is not by itself naturally trivial. And this sampling theorem proves that you can be very precise about what you need to do. It says that if the function that you're trying to sample, that you're trying to read as often as needed, but please not more often, that you need to read that every 1/2 times the maximum frequency that is in the transfer. So if the function is frequency limited, it has no frequencies higher than a certain value. Let's say you take a video signal that runs your TV screen. That video signal goes to a few megahertz, and from there on there's nothing in there. If I read that, if that is megahertz limit, if I read that 4 million times a second, then I read it sufficiently fast, and I can find the signal at any time precisely with the proper interpolation with the sync, if that's what I would want to do. Most likely that's not what I want to do. I'm not particularly interested in that function. I'm interested in a specific property of that function, and I want to be sure that I read it sufficiently often so that the time average of that property will grow as well as possible with the minimum amount of noise. So I want to get all the information out that I can. And I can then treat these digital samples in the way that I think is right by once I have sufficiently densely sampled that function. So the sampling theorem is something that you will see all the time. Mind you, that is not the same as a completely always available foregone conclusion. If I have a telescope which is looking at the sky, then we know that the spatial frequencies up there that we can look at are limited by the size of the telescope. The maximum frequency on the sky is the diameter divided by the wavelength. Faster wiggles than that are not in the image. And so that function of the sky is completely bandpass limited. But I've done that myself by having a telescope of only this size. Going the other way around, if I think of the image that I'm trying to see, you can straight away see that that image in fact has much higher frequencies in there. And so basically I did not sample it sufficiently precisely. But let's go to, for instance, a stellar spectrum. Stellar spectrum describes the intensity as a function of wavelength. And there are features in there which are caused by the atoms and ions in that stellar atmosphere which is radiating to us. And as the temperature in the stellar atmosphere goes lower and lower, the higher you go, if you have an atom that has a transition at a given wavelength, then that atom will be effectively much bigger at that wavelength than it is at any other wavelength for the interaction with that light. Therefore, you're looking at the star more superficially in the wavelength of that atom than next to it, and therefore you're looking at the colder star, so the star will be fainter at that wavelength and broader elsewhere. That's a way of putting it, that's how you get the spectrum. That spectrum therefore has features in there, and those features of course are determined by the motion of these atoms. That atom might know precisely which wavelength it wants to absorb or emit, but that very precise wavelength of course gets altered by the fact that some atoms go your way and other atoms my way. And therefore, if we go, widely speaking, a kilometer per second back and forth, statistically, then the line cannot be narrower than 1 kilometer per second, which is 1 part in 300,000 of the velocity of light. So a resolution of better than 1 part in 300,000 does not make sense, because I don't see anything that I didn't know. And in fact, that is very optimistic, because most likely the star, by rotation, will make that much wider still. So in that stellar spectrum, usually there are no features, particularly if the star is very hot, there are no features in that stellar spectrum that are interesting at a resolution of 1 or 2 kilometers per second. It's usually 5 or so. So that thing is band limited, and therefore you can see that you need to sample it only every so many angstroms, nanometers, or fractions of nanometers in order to get the full sample. And therefore it specifies the resolution that you would like to have from your spectrograph. And that it specifies all there is to know from this stellar spectrum, because you know ahead of time that it is limited in its frequency content, if the frequency is the number of wiggles in that stellar spectrum. I'm purposely explaining that in other terms of space, it's not only time versus real frequency, but it's also position versus wobbles that you have on the road, for instance. A road with a high spatial frequency, when you're going on your bike or your roller skates, whereas a road that's very smooth, even is smooth with very small wheels, because it just is smooth, and it has very little frequency content of spatial frequencies. So I want you to realize that the inverse domain of a position, or an inverse domain of time, and so on, those inverse domains are the ones that you are sometimes describing if you want to go to the other domain of a Fourier transform. Well, that about the Fourier transform that we had. Oh yeah, I should correct still. I'm very sorry, someone pointed out to me that I did that wrong, and that's right. I should have said cos and sine of, no, come on. There we are. Cos of pi x and sine of pi x rather than the 2 pi x there. And therefore, the 2's here and the halves don't fit together. I'm very sorry, and some of you must have spent a lot of time just finding out that I did it wrong. I'm very sorry, that's the wrong way of spending your time. Super, thank you. So that is, again, about this sampling function. It's good to realize that it is specified as a sum of all sorts of delta functions. Mind you, delta functions, it's good to realize once and for all, delta functions are bullshit. are no formal proper functions. They're silly things because they're zero all over the place, so basically there's infinite number of zeros in there. There's only every so often it happens that the number is rather infinite rather than zero. And that is, of course, for a mathematician completely wrong. Anyway, a number like infinite doesn't exist for a mathematician. But this infinite is only relevant because it is made such that the integral from just before until just after, from this one zero here to the other zero on the other side, that integral is unity. That is the only thing that has achieved, and the reason why we need it is that helps us describe sampling. Either a single sample in the delta function or a bunch of samples with the sampling function. But the proper way in which you describe that in reality, of course, is you have some function which is very close to infinitely narrow. And with infinitely narrow, you mean narrower than you can see. That is not the same thing as infinitely narrow. And that narrow function, therefore, has a Fourier transform that does not go on to infinity. So the unity of the Fourier transform of a delta function, that already was there well before the universe started. It is going on until way after the universe has died. That is not particularly interesting for us. If it started last year and it lasts next year, then that's just as infinite for both processes that we are describing as the other one. But that, of course, does have a Fourier transform which has a width, the proper function. And the fact that I sample with that, I multiply the function by that thing so that the integral from just before it till just after it is just the function value is exactly what I want. So it is only an artificial way to describe it so that it hurts for definitions of a Fourier transform or for integral relations. And that's why it's important for you to play with delta functions and sines and cosines and block functions, which are all functions that are not truly physical. You must realize that they're just usually almost good enough representation of what you want to describe in a physical sense. By the time you start leaving that this function is truly infinite up there, or that there are true up cutting corners on the block of your block function, by the time you need really, then you are the troubles that mathematics can tell you. But those are not very physical sort of requirements. Okay, so that then turns us into the trick. It is very important to realize that the multiplication of this function with this sampling function, which provides us with this thing, that because of the multiplication turning into a convolution, the other domain produces this thing as a set of delta functions again. These delta functions are convolved with this Fourier transform of the function, and therefore I get this function here, and I get it yet another time here, yet another time here, yet another time here, because that's the convolution of this repetitive function with this single function here. This is not particularly interesting. It usually is troublemaker. The fact that it's there and yet another time and yet another time and yet another time and yet another time. And that it can be a troublemaker, you can see straight away. If I do not sample sufficiently frequently, so I bring the sampling a bit further apart, or even that far apart, then yet another time and yet another time and yet another time starts overlapping. Then I don't know whether the output here is caused by that wing or by the other wing from the other side. And therefore I cannot get the original function back precisely. So this is a way of freeing information But that's of course clear. You can imagine if I have a function that wiggles like that and I take a sample here and there, too far apart, then obviously I'm destroying information. And this repetition then therefore is not particularly relevant, and I can just throw that away. If I make a Fourier transform of the data that I sample with the interferometer, that we will look at in more detail, I do that by making a Fourier transform and then I have the picture of the sky. But if I do that on a rectangular raster of delta functions in both the x direction and one in the opposite direction, in the y direction, I've sampled the full plane and I make a Fourier transform, then that picture that I'm making repeats and repeats and repeats again, and it does also the same thing in the other direction. And what you must make sure of, if that picture is sufficiently far away, that the tween is sufficiently clean and the overlap is sufficiently feeble. But the problem is that the overlap is still there. Because in reality, I have been looking with my single dish telescope at the sky, not only at that part of the sky of which I was sampling the Fourier transform, but I've been looking at the whole sky, be it with a very low sensitivity. So that thing comes in the wrong sense. So there are effects in there that are in the domain of the overlap. And that's very often that you will see that you do violate this Nyquist sampling for some unavoidable reason. However, you can budget that properly and can make sure that you're not hampered by it. But you must always make sure that the function that you have been sampling, that is indeed specified properly as a bandwidth limited function, and it usually isn't. Okay, there's another part of the Fourier transforms that we hadn't covered, but it's rather straightforward. You, of course, need to do Fourier transforms in 2 dimensions. And that is very practical, as Fourier transformation is completely linear. You can see straight away that you can Fourier transform in the x and the y direction separately. So I do the Fourier transform in x, then I have a function in frequency in the x direction, but still in position in the y direction, and then thereafter I can Fourier transform the other direction, and that's completely healthy. For the same reason, we also must specify a 2-dimensional convolution, and again, I hope you notice that the argument gets reversed in both directions. And a few more of these functions that need to sometimes be specified in 2 directions. This one is rather a nice weirdo. Either you take a pi of x times a pi of y, a block function in the x direction, times a block function in the y direction. That makes you a nice cube at the origin. But you could do it differently too. If you take a delta function of x times a delta function of y, a pi of x times a delta function, convolved with a pi of y times the delta function, which is just a very thin sheet, convolved with just another very thin sheet, delta-wise, and that also makes this block. So you either make it this way as a multiplication or as a convolution. And it's good to realize that that comes out as completely the same way. And the 2-dimensional cross correlation is also specified, and there you can have the effect of both the x and the y in a function come into the correlation coefficient. very special case comes about now, because we are now doing a two-dimensional thing, then symmetry about the rotation axis comes in again as a possible aspect. And it is called a Hankel transform if we now go into a new coordinate system with the radius from the center of symmetry. And then you get, if you find a ring like this, then you get a ripple. If you make a cross section for this, this is a ripple sink, but then a two-dimensional sink, a rotationally symmetrical sink sort of thing, as then called a J1, a Bessel function. That is because now the weighting per unit area comes in, whereas first we were weighting per increment in X or per increment in S. Now we're weighting per square centimeter or per square decimeter. And so the weighting as a function of distance goes down quicker than it did before. And therefore we now have these weirdo functions, Bessel functions, but they look like a bit like a rotationally symmetrical sink. And a specific one that we have been already used to is the Fourier transform of a disk. A telescope basically is sampling all these Fourier components up to a certain spatial frequency, and that's the end of it. From there it doesn't do that anymore. So that is sampling a disk. And that one becomes a Bessel function of the first order, and that becomes then a J1 of X, or an Airy pattern. We can think of special functions like delta functions in one way, or in two delta functions here. If you have symmetrically with respect to the origin two delta functions, you think straight away of, shoot, that must be a cosine sort of thing. But it's even, it's on either side of the origin. And of course the cosine then as a ripple lies in the direction that's specified by the location of these two delta functions. So I can rotate this system by rotating these delta functions. You can also understand straight away that you have a cosine times a cosine if I have 4 of these delta functions. So I can make a two-dimensional ripple by having these 4 delta functions. And of course I can also make a comb of delta functions, which are now fences, one-dimensional fences. And of course this thing can also be rotated, and this thing will rotate along. But it's good to realize that all what we have said in one dimension can relatively easily, certainly in terms of imagination, be forwarded to the second dimension. Of course then you would also again expect that a single delta function at the origin does something like unity in the other domain, so it gives a fixed level in the other domain. Again, perfectly illegal, because this thing of course is not integrable, and this thing is now for that reason, because it must be integrable in both coordinates at the same time. This is infinity squared to make it work, so that the integral still becomes unity if I go from minus epsilon to plus epsilon in X and in Y. But that is completely irrelevant, as I said before, because this fact that it goes all the way to infinite is not the relevant part. It does not go to fully infinite, and therefore it is not infinitely narrow, but it is so narrow that I can't see the difference. And then it does whatever I like it to do, and that's good. So whether I have in reality or conceptually a delta function which has a width of a human hair or a cat's hair or a straw, doesn't really matter as long as if I have described it better than to the nearest meter, and it's perfectly adequate. And whether this thing goes all the way to infinite and be infinitely narrow, or it is a bit wider, doesn't matter. And so these delta functions are just a bit overstretching the issue that you mean just a specific value, and you do not usually specify how precisely you mean. If you're specifying that you want 10,000 pesos, you sometimes really mean 10,000 point more pesos, but in most cases you will mean about 10,000 pesos. And in general, numbers mean something to a given precision. And that's exactly what you're trying to do and specify by means of these delta functions. The delta function is more precise than what you want to specify. So you don't mess it up by the delta function. That's the only thing you specify. That was it. Now we have basically gone through the formal theory of Fourier transforms to the point that I hope you sort of understand how they work, and making them is an art in itself, and I don't think this course has the function of teaching you that. In fact, there is no way of teaching you that other than that you go and train yourself. So by the time you find yourself in need of being handy in Fourier transforms, you will just have to do it, and then it will come about relatively easily. What is important though is that you can think from one side to the other and back. And that's why I have a set of pictures which I think are rather interesting in that respect. There's a guy in York University in the United Kingdom who's made nice pictures of Fourier transforms, which he has even color-coded so that he can give the real and the imaginary part in one picture. And I will show you a set of pictures just to get you feel for going back and forth. A raster of delta functions is one of the things that he has looked at. And the first one that you see there is just two delta functions. These two delta functions Fourier transform, of course, and you must be aware of that, into a sinusoid, and where they lie with respect to the origin specifies where the sinusoid lies. But it does only a sinusoidal pattern. If I put more of them in there, they start interfering, these sinusoids start interfering with each other. And that's why you get this nice ripply pattern in different directions. If I do the same thing, but I put more of them in there, then I get the same ripply pattern, but interfering with more stripes. And therefore it gets more structured. If I put them further apart, then the stripes get closer. So all these steps here should be perfectly natural for you and exactly what you had expected. But now let's try and turn that into something that's a bit more pictorial. Now this is a delta function in its early stages of definition. It still has a significant width. That's why it's a bit softish. And the Fourier transform of that thing makes sure that the far distance in the other domain comes closer in too. So suppose it's a Gaussian. One of the ways to define a delta function is by means of Gaussians. And the Fourier transform of Gaussian is another Gaussian in the other domain. If you make it broader and broader in the one domain, it gets narrower and narrower in the other domain. That's exactly what you're seeing here. Now if I have that same thing a bunch of times in some pictorial fashion, then that gets all sorts of interferences from these different things in terms of amplitudes and phases. So it becomes a rather weird pattern. That pattern, if I repeat it another time, becomes periodic on top of it. And if I repeat a bunch of times, that I get more and more structure, you can still see the original Fourier transform in here of each of the spots. Now we make a nice picture of this nice little ducky. And the Fourier transform of this little ducky looks like this. And you see there's a significant amount of imaginary in there. That's of course completely understandable because this is not an even function. It has odd components too, so it must have imaginary ones in the Fourier transform. But perhaps I haven't got enough space to note all these numbers down, and so I think, well, getting the part just around the origin should be sort of good. That's a bit what we do with the telescope again. And lo and behold, my picture gets fuzzy because the high space frequencies are clearly specified. So this is what you call a low-pass filter, a rather brute force low-pass filter. I just throw the higher spatial frequencies away. And that kills this pattern rather badly. You could also do the opposite. Throw this one away and leave the rest. And lo and behold, you get a beautiful duck, except for the fact that you have not described the intensity properly. And therefore, the duck has all sorts of features that suppress the height of the signal, but the details, the high frequency details are in there, so the duck is very precisely depicted. You could even do other things which are completely normal in the applications that we will see, like incompletely measured Fourier transform planes. I will picture an annulus of data. That's a specific set of data on a specific spatial frequency that I do not have. And as you would expect, I suppose, is that is a multiplication with a, that's a multiplication with a function which is unity all over the place and 0 in there. That function has a ripple, rotationally symmetrical ripple, which is the convolving function of the picture that I wanted to get. And indeed, that is the way I got all these ripples centered around the duck. You might also do it completely proper. However, you throw away with dice every 10th data point. So 1 in 10 times you make sure you have a dice with 10 faces, and if the red face comes up, you throw that data point away. And you do that for all the data points. So I randomly reject data points. You can hardly see the difference of this picture with respect to the original picture here. If you compare this one to the other one, you cannot see it. But what I have done there is something real bad, because I have in some places put 0 where I should have put the data. And putting 0 in there is a very erroneous number. And because 0 is an erroneous number, I get ripples of all these tiny little delta functions times error. Because if I should have put 17 in there and I put 0 in there, that's a delta function times 17 that I have subtracted at that location. Now Fourier transform is linear, so the ripple of that one that I didn't put in there is now in the final picture. And that is for all the things that I left. And that is the reason that it basically makes the whole picture noisy. It puts power from the image of the duck all over the place. And this is only 10% missing. If I do that systematically, I do that basically in rings. You can see that here a bit. So these points are missing, but sort of centered on the rings. Then the effect becomes much more regular. So the more regularity I make in my errors, and errors is not only making the wrong number in there, putting 0 in there because I didn't have the number is also an error. It's very good to realize here that before you make your Fourier transform, you must decide on what you do about what you have not measured. Because specifying that it is 0 at that location is wrong. And yet you do that by doing the Fourier transform. You can see that effect very badly if I cut out full sectors of the Fourier domain. This is a very realistic situation. An interferometer. I'm observing an object as it comes out of the horizon, and it goes up there and it goes down again under the horizon. And this object is on the other side of the equator. I cannot observe it for the full 180 degrees, and then it's gone again. Therefore, I'm necessarily making parts of the Fourier domain unobservable. Well, I don't, the Earth does. It sits in my way because I can't look under the horizon. But I cannot observe it. I must go to the other hemisphere if I want to observe it. And so this thing does happen if I observe with the telescope in Westerbork an object like a planet or so, which happens to be in the southern hemisphere. In fact, we did extensive observations of Jupiter in '73 with Jupiter, unfortunately, very far south. But that was the time that Pioneer flew by, and we wanted to try and have good observations at the same time, which we could then compare. That was a quite interesting project. The project led to the thesis cum laude of Professor De Pater in Berkeley nowadays. She's of the institute there. But that was with Jupiter at minus 20 degrees declination, so we could only observe from about minus 3.5 to plus 3.5 hours, hour angle. And that left such a big hole in the UV plane, in the Fourier domain, which you will get to know as the UV plane. And you see how that badly affects my image of my little ducky. The question now is that recoverable? And yes, fortunately, it is to quite some extent. We will see all sorts of measurement and data treatment techniques that make use of information that we haven't used yet here. There's lots of negative numbers in here, and we know for sure the sky doesn't shine negatively. So we can exploit that. It's not so trivial to actually turn that into an operational constraint, but you can make these things come about and make proper operational constraints, but we'll come to that. But it's good to realize what happens in the Fourier domain back and forth if you do something wrong, or not wrong, but unavoidable in one domain. Like here, we have this nice little catlet, but I'm very sorry, I've lost the phases. So this is the amplitude only picture. And this one back makes nothing. So this is the picture, and I lost it. Now, I fortunately have another cat, but it doesn't have a tail. But it looks rather alike, so I could try and use the phases of this cat with this amplitude and see whether something comes out then. And so I used this Fourier transform with these phases, which are derived from this guy. So, sorry, this one with phase from this one in here. And lo and behold, I get something back that I would have expected. Because this tail is uneven, right? There's no tail on this side. But I have no information about that tail other than it's sitting here. And it sits not quite in the phases either. So I'm trying to replace that tail again in a sort of even way. And that's what you see above the head of that cat. Because all the information about that tail is in this amplitude part. Yeah. Go ahead.
What do you mean with repair? I mean, what kind of operation did you do?
I have, of my little ducky here, I have a full Fourier transform that says at each of the locations here, which is a properly sampled thing, so it's a two-dimensional comb of sample locations, I have an amplitude and a phase. That's what the output is of a Fourier transform. It says the intensity is this much and the vector sits like that. And that's the phase. Now phases sometimes are very difficult to. You will see that in interferometry too. There's also reasons why a phase gets stuck. Some people can't recover it. Now I did just dumb. I lost my file of phases. I have the file of amplitude, but I lost my file of phases. That's too bad, but now I don't have it. Can I still make my cat? No, I can't, because I need the phases. Oh, but I have a thing that looks a bit like cat. Shall we try and use those phases here? See whether I can get the original one back, because I'm pretty close. And you see exactly what you would expect. The only information about that tail can only be in these amplitudes because this guy doesn't have a tail. Must find that the amplitudes describe this little tail, and it does. Not very well, and even worse, it has a tail. Try it even because amplitudes are the even part of the story. A phase tells you about the odd part. You get the point? Doing something illegal. I'm trying to make sure that we understand how illegal that really is, what I'm doing there. Like leaving points out, it's also illegal, and that looks completely natural. Sometimes that happens. I'm doing, what is the effect of that? Even worse example is this one that's really funny. I have this duck and I have this cat, and they have both very nice Fourier transforms. But I put this aside as amplitude files and phase files, and I did something dumb. I swapped them. Now I have the nice duck amplitudes with the cat phases. And sure, it is not a very good cat. It certainly is no duck. And the other way around, exactly the same. I take the amplitudes of the cat and I take the duck phases. And it becomes much more duck than cat. The fine details of where the flux originated, where the picture originated, is described in the odd part of the story in the phases. So you lose very much about the picture if you lose the phases. I have yet another one. This one was very nice. Sure. I have a very nice Fourier transform of duck. In fact, I also have a very nice Fourier transform of cat. And I put them in the cupboard, but I have them as a file of phases and a file of amplitudes. And unfortunately, I forgot to label them properly. So now I put them back together, and out comes a very silly image. not at all what I expected. And I look better and I find out that it is because I used duck amplitudes plus cat phases. And that made a picture which is basically cat, although right, and therefore I have errors all over the place. The other way around is again the same thing.
Talking about amplitudes and phases,
yes,
is more or less the same that talking about the real part and the imaginary part. Of course they are related, but I was thinking if we can think also as throwing out the real part and just keeping
yes,
the imaginary part.
I'm sorry I haven't got an example of that. Would do that too. And I'm pretty sure that it would even become more awkward, because with the real part, obviously, you're looking at only the cost transform, and it's completely even. There is no way whatsoever that you will be able to see the difference between flux from there or from there. It is rotationally symmetric around the origin. Whereas you look at the sine transform only, it will only depict every part of my picture that is different there and from there. It does only the odd part.
So if we keep the real part, we keep the symmetrical aspects of the duck and the
yes,
cat, and if we get just, okay, great.
The point is that in the phase is the only location where I have the uneven part described. The amplitudes do not seriously describe an uneven part. In fact, they do not describe an uneven part by themselves. So basically the amplitudes are even, not quite, but a good question. Can someone tell me what this is? It's only the amplitude of a object of which we made a nice picture, and we threw away the phases and then made a nice picture of the amplitude. There must be something in there, sorry about that, something in there that organizes these specific directions, and then there is something periodic in these directions, and it's rather precisely periodic because it's rather narrow band in these periods, and it's orthogonal to one another. It looks very symmetric, right? But that's, of course, I agree. Yeah. Shall we add the phases to it? Let's see what you get when you Fourier transform it. But you can do again the same game as we did with the cats and the duck. We can play this game also with phases only, amplitude being unity all over the place, and only phase, or we do only amplitude. And you see that in the amplitude you lose completely the pictorial information, you get only the symmetry part of the information. And in the phase you get the picture all right, but with all sorts of errors because of the amplitudes not being right. So it is crucially important to phase information if I want to get proper images. And that's the point I wanted to drive home. And you will realize, and you will see more and more, the further we get down in the course, the more we are discussing how awfully difficult and troublesome it is to get proper phases. Getting interferometry is in very many bound getting proper phases. The first success is, yes, I can see fringes, because that means that the object is smaller than the size of the wiggle. So I can now say something about the object that I'm looking at. That is already a success. But if I then want to turn that into images, then I do need phases, and that gets even more difficult. And I wanted you to get a good feel for that. Okay, that is as far as, oh no, I want one more thing about Fourier transforms, and it is how you calculate them. You can calculate them according to the definition. So you just evaluate all these different products, the definition. And that is the natural way if I have a Fourier component here and a Fourier component there and another one here and another one there. And I have 10,000 of them, and then I want to make a picture. But if I have a Fourier sample set on an equidistant regular grid, let's go back to such a regular grid. Where was it? I stepped past. I stepped past. There was one, I thought. No, only one dimension. But I can, of course, do this, extend this thing to a regular grid, a nail bed, say. If I have a Fourier or if I have my data on that regular grid, there is a trick which makes Fourier transform calculation a lot more easy. So if I have a proper regular raster, then the number of calculations, which was n squared, that's very bad because I have 512 by 512, 1024 squared, let's take that one, that's 1,000,000 calculations of a Fourier transform, 1,000,000 points to calculate for each new point that I want to do, and I want 1,000,000 of those. So I get 1,000,000 squared operations before I'm done. If I want a nail bed of 1024 squared, Fourier transformed into this other nail bed of also 1024 squared, we have just decided that they are each other's transform in some way or another. Then, if I do that the classical way, yeah. That's what I'm telling you. That's what this is about. There's a trick which makes that, the trick is not particularly relevant because that's nice number theory and math. It's a trick that was devised, I think, for the first time by Kulityuki about 55 years, 60 years ago. And it sits now in all computers at all times. So the trick is you put your samples that you have of the Fourier transform, which you want them to Fourier transform in the other domain, you put them on a rectangular grid, and then I can reduce the number of operations from n squared to n log n. That is a sizable compression that can easily be 1,000-fold. Yes, sure. No, it's a cheap way once you have written it down. Yeah, exactly. And even nicer, I need it only one-dimensionally because I do the x first and the y thereafter. They can be completely consecutive. You do not need to carry your function around all the time. No, you do breep, and then you do it in the other direction. It's done. So the gain of this trick is colossal. And it must be done. However, I'm making an error there. I didn't have the data at that raster. So if I put them there, I misplaced them. That's going to give trouble. I can assure you it gives trouble. There's only one way, and that is to do a proper interpolation. So I have data points here and there and there and there and there. And now I find a creative way of interpolating that field to a continuous function, which I then multiply with my nail bed to make it rectangular. In other words, what I'm putting in this one spike in that nail bed is not defined by the nearest point here somewhere, but is defined by a bunch of points which define a smooth function and I sample it properly. If I do that, then the convolution of that thing comes back as a multiplication in the Fourier transform that I'm achieving. I must do this convolutional right, and I must undo that multiplicational right later on in order to get back to what I would have wanted to have. However, that is still a lot cheaper, even convolution, than going the whole classical way. Mind you, the whole classical way has this additional advantage that I get only one map, because it's defining properly the Fourier transform all over the place for this one position in the other domain. It has not this problem of the repeated map and map and map that you get from this nail bed. Nail bed Fourier transforms to a set of the same maps in all coordinates. The troublemaker is, of course, the convolution. The convolution is an expensive thing, and it must, in some way, make sure that I can convolve that properly. The standard trick that we use, that possibly we come later on in the process into a more detailed discussion still, but that is about algorithms. The trick that is being used usually is you take a relatively narrow Gaussian, which covers a few points of this rectangular nail bed, and I put my sampled number, I put that underneath that Gaussian, and I read that Gaussian times this sampled number, read it at all the nail bed points that are in there. And at some point I say this Gaussian is irrelevantly small and I throw it away. For that you need a Gaussian which covers of the order of 3 points squared in the nail bed function, if you do it properly. But you must look at, to not hurt later on, and you must then also realize that you have now convolved your data with the Gaussian. Therefore you have multiplied in the other domain the map with the Gaussian. You must undo that multiplication too. So you must scale the Gaussian that you used for the convolution to the map domain and then divide by Gaussian in order to get the map right and properly normalized all over the place. It's cheaper doing it this way, where you do something between 9 and 16 points in the nail bed function with a convolution. It's much cheaper still than doing it completely the classical way, where every point is a full sum of all the relevant Fourier components. Now that we have looked at that, we go by Rick Perley's, and I'll show you this one because I'm stealing from his very good presentation, which I can assure you is worth your while to also look at. I meant to have a slide, and I shall produce that for you soon. The websites of this summer school and yet another summer school as well that I suggested in AstroTwinCoLo for the course, so that you have more references. And then we go back to what we already said, and we go now to the interferometer. So this was the episode of Fourier transforms as far as I'm concerned, and from here on we will sometimes use a Fourier transform, but we will not go and discuss it in more detail unless someone has a specific problem with it, and of course then we go into it. And we will of course go back to looking at the single dish as something like a Fourier transformer, and then we will see how our basic interferometer looks at point sources. That's already quite some story, and how it can also look at extended sources, and how you then need a complex correlator, and that thing that measures visibility. So the name that we attach to this Fourier component is a visibility, and I hope I can convince you why we call that visibility, so that it becomes a natural number. Well, again, this you have seen. interferometry is necessary in order to be not so badly limited by the maximum size of telescopes that we can construct. And so we try and improve resolution by putting the sampled points of the electromagnetic field further and further and further apart and see how they relate to each other. That is cross-correlation. Seeing how they relate to one another. And what you do by making a cross-correlation is you make a Fourier computation of the other domain. And if I do that with sufficient samples and sufficiently different places, then that might turn into a map. That's what you want. And in terms of imaging, you don't need very much more than just a single example of this nature to see that this is not a buildable trick, and therefore you must go the other way. Optically, it's not so clear. Your eye, we discussed that before, can in principle resolve something a bit better than an arc minute. It doesn't quite, so your lens is not quite that good. That is natural, because usually you, in bright sunlight, you have a very narrow pupil, and of course that should, because it's the narrowest pupil, give the worst image. It does not, because it sees so much light, and so it's self-adjusting to some extent. But your eye can see of the order of an arc minute. A telescope, even binoculars, can see much better. But at some point, it fails. You cannot look any better. And that is pretty soon already. A telescope of 10 centimeters, a nice, but not particularly outrageous amateur telescope, was just about as good as the 200-inch in Palomar in terms of sharpness of the image. And that is because the wavefronts, as they come in here, they make it very nice all the way to our atmosphere, but the last 20 kilometers they go through this atmosphere where the density is a bit stochastic, because there's a blob of warm air sitting here. There's fewer molecules per cubic centimeter in here than here, because it's warmer in here, and the other way around. Yes? Oh, sorry. Okay, so then, having stated that we need bigger telescopes and that we need to do something creative about it, we will come back to that in 1.5 hours, so at 4 o'clock. See you all by then. Bye.